Then we are going to continue with the investigating the problem of classification. So we started 2 days ago explaining what the classification problem is and how we provided a few examples and also looked how we could actually analyze the error of a classifier. So given we have labeled data, how can we evaluate if a classification system that we have built performs well on a given data set? So the classification problem in general can be formulated as we have a set of k classes, so those guys over here, and this is kind of some semantic information or semantic meaning that, for example, we as humans assign to, for example, a part of an observation. So we have an image, let's say there are cars in the image, then we want our classification system to say this area of my image, for example, is a car, or another part of the image is a building, so we can add this semantic information. And the input to such a classifier is our features. So these features are called E, and these features can be the raw image as it is, but often we use some kind of features that we extract from our perceptions, from our image data, for example, and do the classification based on those features. And what the output actually is a function f, and we want to learn this function so that we can, as an input to this function f, provide our features, and the output is a class label. So I can put in my image and it will tell me, in this image you see a car, or this region of the image corresponds to a car. And we kind of discussed it last time with a couple of, or with at least one larger example, how we could do that in a very simplistic case, and then analyzed what is actually the error of such a classifier. And today, we want to dive more deeply into that. We'll start with the concept of generalization, and then we'll present 3 different ways on how to obtain such classifiers with different techniques, starting from a very simple one, getting more and more complex. So the first thing is that if we design a classifier, the first thing we do, we have a so-called training phase. And in this training phase, we build up our classifier. It starts with the fact that we need labeled training data. So this is a supervised approach. We have some supervisor, typically a human, which provides examples to the system. For example, what is a car? What is a building? How does it look like in an image? So I really need to sit down as a person, for example, label those parts of the image where there is a building or a car in there. And I have to do that typically for a quite large set of images. This is the first phase, and this is typically quite time-consuming phase. The next thing is we actually need to select and define appropriate features. I'm going to ignore that topic for this lecture today, at least, on how we obtain those features, but the type of features that we actually choose can have a substantial impact on our classification system. So if the features are well suited to make a distinction of the classes I'm interested in, that is of course beneficiary. If the features don't support the separation of classes at all, whatever complex classifier I will add behind those features, it's likely to fail. So we're not really addressing that, but we need to define some features. So if you, for example, look to the chapter of binary images, we defined a couple of features on binary images, the connected components, the area, the parameter of, for example, those objects. And we could use those as features for simple classification problems, like, for example, character classification or digit classification, so handwritten digits. We can use those features to actually determine, to classify, based on the binary image, what kind of digit is written down, as an example. If we go to more complex tasks like analyzing real photos, we typically also need more complex features. And then the main task is also the task we are mainly interested in here, is learning a classifier. And that means we learn a distribution of features, so how likely is a certain feature to occur, given we are observing a certain class, or a so-called discriminative function, which allows me to separate one class from the other. So one thing is to learn the full distribution. So how are the features distributed given that I see a house, given that I see a car, given that I see a person, and then make a decision based on this distribution. Sometimes it's easier to simply learn a separating function. So if you have a 2D function space and you guys here are all instances in this 2D space, sometimes it's easier not to describe you, let's say, as a sum of 4 Gaussian distributions as you're sitting here. Sometimes it's easier to just define a separating line or plane, say everything on that side is class 1, everything sitting on that side is class 2. So there are two options which we can take. Either we learn really the distribution over the features, how they occur in their own space, or we learn a discriminative function. Okay, so this is a training phase. So we have given training data, and we learn this distribution or this function. Then what we often have in practice is a testing phase, also called validation phase. So we have a new data set. So on a different data set, or on different data sets, even more, we want to evaluate how well our system works. So what we do, we extract features, actually exactly the same features we extracted in the training phase, and then we use the classifier we learned before, so the discriminative function or our feature distribution, to determine the class of those features. And then we evaluate the performance. Typically we do this evaluation on a data set for which we also have manually given labels. So we know they have the ground truth label and can compare it to. But the important thing is that this data set used for the evaluation has not been used for training. Otherwise I would just evaluate what I have trained before. And maybe I do a couple of iterations, maybe changing some parameters, choosing a different classifier if I see that the performance is bad. When I'm done with this phase, I'm ready, my classifier is ready to go. What I then do in the operational phase, I just do the first steps of the evaluation phase. I get my new data in, the data I'm really working on, so there's no learning involved anymore. Just extract my features as in the training phase, and I do my classification decision. So that's how the system works. So basically, we can actually split that up into two phases. This is the operational phase, and this is kind of testing and learning phase are kind of tightly coupled. But the important thing is that we need to use different data sets for training our system and then evaluating how well it performs. The reason why we need to do that is because the most important thing we are interested in is actually generalization. So if we say, because the important thing is that we provide a set of training sets. So for example, we have whatever, apples, tomatoes, cows, horses, dogs, horses, or whatever, and we want to distinguish those classes. And then we have, this is our training set, labeled, and then we have a test set. And so these are different cows. This cow is different to all the cows we have seen before, but they're kind of similar. And the generalization capabilities of my classifier is how much can this cow, or the appearance of this cow, actually deviate from what I've seen before. Of course, if this looks completely different, it's very unlikely that I will actually say this is a cow. But typically we are interested in systems that generalize well to different appearances of cows, although we have just seen a small subset. And therefore it is important that I do the learning of the classifier and the evaluation of a classifier on different data sets. If I would use the same data set, I would just need to store those cows and compare those images. That would be trivial. But I'm interested in generalization, so I'm learning on this, I'm testing on this set, and then maybe say, oh, the classifier I've chosen may not be a good decision because it performs so badly. Maybe I need a different classifier. And once I'm happy with my evaluation, say, I'm done, now I can deploy that and use this for the classification task I'm actually interested in. Okay, if you need to generalize, we have to make assumptions. Without assumptions, there's no generalization. And what we typically do, we have some kind of model on how our classifier looks like, and the generalization error of this classifier has 2 or 3 different components. The first one is what is called the bias, and this basically tells me how much the average model that I learn based on different training sets. Let's say I take 10 different training sets, I learn my model on every individual training set, the average of those models, how far this is away from the true model. This is kind of the bias that I have. And the deviation of the true model and the model that I learned, or the average model that I learned, typically depends on the fact that I make simplifications. So let's say I have a classifier which is given by a set of points in 2D, and that I could fit a parabola through those points that would explain it well. However, my model assumption is that it is a linear function. And as the linear function has less parameters at the parabola, I cannot represent those points well. It's likely that I can't do that well. And this introduces such a bias. The next thing which is important is a variance. And this describes if I train my classifier on different data sets, how much do those models vary? So if I kind of train on data set 1, on data set 2, on data set 3, data set 4, and so on, how much do they vary? How different are the obtained models that I estimate from my different training sets? So as a small example, so if these are the data points that I have, the red dots, and this green curve over here would be the true model. My model would be the true, representing the true model, or the right model. I now say, okay, I'll just fit a straight line through those points. If I fit this straight line through those points, I need less parameters, but it's clear that this is the average model. There's a deviation from the true model. And this introduces a bias. So if my model is too simple, I don't have enough flexibility to actually represent my data points. On the other hand, if I say, okay, if my model is simply too simple, I give them a large number of different parameters to optimize it. In this case, I may fit a function like this blue function to my model, which actually nearly passes through every of my data points. I could even add more parameters and it would fit every of those data points well. Then I have the problem that I'm basically fitting my model to the noise that I have in my training data. And as a result of that, something which is called overfitting. I overfit to this data set. And as a result, if I use a different data set, so a couple of slightly different red points, I will also get a different function. So this introduces a large variance. Typically, I'm interested in low bias and low variance. So I need to come up actually finding the right model. This is my goal. So the expectation of the mean square error is given by 3 components. One component is the variance. This was the variance that we discussed before, because my model is too complex. I have too many parameters to which I fit my, which I use to learn the model from my data points, and as a result, I kind of fit to the noise in the training data. Or I have too many assumptions in there, I'm too very simple, and this introduces a bias. And the third term is kind of what's called noise, or the unavoidable error that I, of course, may have. For example, if I take an image, my sensor has a certain amount of noise. I can't get rid of that noise. These are kind of those 3 elements. I can't do anything about this, but I want to get those guys as small as possible. There's also something which you find in the terms of underfitting and overfitting, which we can express here. So, yeah. Yeah.
Is 2 on top of noise and pi?
Square.
Index or is it really squared?
It is squared. So the noise would then be standard deviation squared. So I have two things here. One is called the underfitting, and overfitting are 2 things which we often experience if we learn classifiers. The underfitting is that our model is too simple for representing the distribution of features that I have in my space. And this typically leads to a high bias, but a rather low variance. So even if I take different data sets, I would typically end up having a similar model. And if I evaluate the error that I obtain with my classifier on my training set, it will be high, but it will also be high on the test set. Because simply my model is too simple, too simplistic in order to come up with with an appropriate model that allows me to describe the distribution of features well. On the other hand, overfitting is often something which happens often here. I have too many parameters. Simply choose a model with too many parameters, so that I'm basically overfitting to the noise that I have in my training data. This typically leads to a very low bias, but a quite high variance. Because if I train it on a slightly different data set, I will get a completely different result. As I'm coming off overfitting to my training data, the error on the training data is high, but the error on the test is low, sorry, but the error on the training data is high. Because I use a different data set now, and my performance gets bad. So this means I'm not generalizing well. I kind of overfit it to the data set that I have. So as a rule of thumb, if we define classifiers, the first pretty good choice is actually try the simplest classifier first, see how it performs, and then Only if this does not perform very well, use increasingly complex classifiers or powerful classifiers, for example, with more parameters, in order to see how the data performs. And also one thing is, if I need to fit a large number of parameters to my, for my model, I typically need a large amount of training data. So if I have only a small training set, it doesn't make sense to use a very complex model. Of course, typically need, so the more parameters that I have, the more training data I need, as rules of thumb. And the last thing also that's not really addressed here is actually find good features. The better features we have, the simpler our classification task will be. So it makes sense if I'm interested in a particular application, solving a particular classification problem, to invest some brain power in the question of which features should I actually use. If I select good features, classification becomes easy. If my features simply do not allow me to separate the classes I'm interested in from each other, no classifier can actually solve my job. Again, also no classifier is inherently better than any other classifier. All classifiers make assumptions, and we need to make assumptions in order to generalize well. Without assumptions, we cannot generalize to unseen stuff, because we just have a few instances and we want to generalize it. So we need to make assumptions like, whatever I see must be very similar to what I've seen before, for example, in terms of color in an image, or in terms of gradients in the image, or in terms of extracted lines in the image. These are the assumptions that I need to put in. And we have three different types of errors. The noise, we can't do anything about. This bias and variance, which we would like to reduce. So how do I address the problem of evaluating a classifier, how well it is actually performing with my training set and test set? Because in the practical approach, it's we collect a set of data of labels, label training data, and now I say, now I have this training data, how should I actually evaluate my system? I could train it on the whole data set, but in this case I have nothing to test against. I can say I can take only a small part of it and then test on another part. How should I actually split that up? And there are a large number of different ways on how to do that. One suggested choice, so cross-validation is one family or one type of evaluation one can do, and there's this 5-2 cross-validation, which is quite frequently used. It works the following. We take our large label training data set and simply split it randomly into two parts of equal size. Then I take part number 1 and train my classifier on it, and I take part number 2 to evaluate how well the classifier performs. And then I swap both of them. I learn on the second data set and evaluate in the first data set. And I repeat this process simply 5 times. Then I basically learn 10 different classifiers and do the evaluation how well they perform with the techniques we discussed on Tuesday on how, if this classifier actually performs well or well enough for my application. So it says, why 2? Why do I split it up into 2 parts? Why do I do exactly 5 folds, or this 5 runs, also called folds? So I split it up into equal sizes to avoid that I, let's say, take a very large training set and evaluate it on a very small set. So I do this setup, let's say, I want to have an equal size training and test set. Why do only 5 folds? I could also do just 2 folds or 100 folds. The thing is that the training data does not change, and if I take, let's say, repeat this process 100 times, I will end up having similar data sets, so they're very dependent on each other. If I do less than 5 times, then I typically may have not enough variation just because I splitted them in a kind of suboptimal way. So this 5 is just a rule of thumb, but you can actually show that if you take substantially less folds or if you take substantially larger number of folds, you don't perform that well. So there's kind of one of the standard procedures to do this kind of cross-validation to evaluate how well does my classifier perform. Once I'm happy with the performance under this approach, I basically ship my classifier, say, now it's ready for the operational phase. Okay, are there any questions about what we discussed so far? That we have these different phases for the classifier, and we talked about generalization and what impacts generalization. I have to make assumptions. My model shouldn't be too simple, shouldn't be too complex, and there's a certain type of noise which I can't get rid of. So this was kind of the key ingredients so far. Anything I can clarify at that point? If this is not the case, we go a step further and look into classification systems and see what kind of different classification systems are out there. We actually will investigate 3 different classification types. The first one is actually nearest neighbor classification. It's a very intuitive and very easy, or probably the easiest classifier I can actually find. It has also some nice properties, so it's actually not too bad for a lot of applications. So the idea is to say we don't explicitly model the distribution of features in our space in the sense that we use, for example, a parametric form or a Gaussian distribution or something like this, or a sum of Gaussians, in order to represent the distribution of features in my space. What I do is I just keep all my training examples. Like in the image I've shown before, the images of the cows and the dogs. And when I get a new image in, I just compare them with all other images and say, I assign the class of the image which is closest to it, which looks most similar. Doesn't necessarily has to be the full image. Typically do that on the feature, but if my image would be my feature vector, then I would simply compare images. So let's say I extract all the corner or all gradients that I have, which are larger than a certain threshold. Then I simply compare those gradients, how they occur, and then say, this is most similar to this one. Or just take color information. I have an image, and let's say I have vegetation and non-vegetation. If I look to color, and the color, say, how green is the stuff, you don't perform that badly. I also have one example which kind of may nicely illustrate that. So this is an image from the Rheinaue, actually, the satellite image from the Rheinaue here, taken with a near-infrared camera. And what I want to do is I can label certain parts of the image. Say, okay, this is water, this is vegetation, this is part of an urban environment, and then say I have these 4 classes, and my colors are simply whatever the infrared information and the green channel, for example. And I say, okay, let's see how well such a system performs. So how do I learn a nearest neighbor classifier based on that? So the first thing I do is okay, these are kind of all greenish pixels. So they take those images which are labeled. So these are my manually given labels. So they populate the feature space somewhere here. These are kind of just 2 channels from this image. And then I can add the others. So the red ones which were here and the brown one which were here. So just add them. And so here's a larger variation of intensity values in the different channels that I find here. Compared to the green area. So they are more compact than the red ones. So this is kind of whatever, water, grass, urban environments, and here the sides of the river. Okay, now I took all my features and put them into my, in this case, 2D feature space. So at that point in time, learning is already complete. That's all that I have to do. I just store the feature occurrences with the corresponding label. Yeah. So these are the spectral bands of the camera. So like RGB, or it was near infrared, this was the first one. So just basically take 2 out, in this case, just to visualize that well, 2 out of the 4 channels of that camera. So you have red, green, blue, and near infrared. And this is, I think, blue near infrared. I don't know. Near infrared, the other one, I can't remember. Okay, so, but you could also imagine that as a 4D. It's a 4D space. The only thing I can't draw that very well in 4D. So if you would take all bands. Okay, at that point in time, learning is complete. So there's nothing else I need to do. So if I now get a new sample, let's say I want to know what is this area over here. What I simply do, I take this value, map it to this space, and simply say, okay, let's say this will end up being this point. What is the point which is closest to this one? This one, or this one, or those down here. And I simply assign the one which is closest. Okay, so let's take those 2 points. I have this point over here and this point over here. One ends up being here, the other one ends up being here. And then I simply do a nearest neighbor search and say, which of my known points is closest to this one, and which of my known points is closest to this one? So in this case, I would have get this type of assignment. And then I simply say, okay, in this case, this pixel or this point over here in space would be urban, and this one would be vegetation. Okay? So it's a very, very simplistic approach. I don't need to take into account what kind of distribution those features may follow. So they look as if you could also represent them well, let's say, with a Gaussian distribution. But they could have, in theory, a completely weird shape in this feature space. And either a designer as a user don't need to take all of that into account. The only thing I need to do, I just need to store all those elements, maybe in an array or in a list or a vector. And if I get a new data point, I just do a comparison. I just compare them with the Euclidean distance to what I know. So it's very, very simple to implement, at least in the easiest version. So you can do this. This neighborhood query is also a bit more complex, but in the most trivial implementation, in MATLAB, you will just, let's say, store a vector of green points, a vector of blue points, a vector of red points, and a vector of brown points. When you get a new data set in, you just do a nearest neighbor comparison. Once you found the nearest neighbor in feature space, that's it. It's the same class. In which situations does this approach work well? What do you think?
Distinctive islands to do this, because if they grow too close together, it will be hard to make application.
Exactly. So I need to have well-separated classes, or well-separated islands in space. This is an important point. What else? So the noise shouldn't be too large. So even if, let's say, they are kind of a little bit close, like those guys over here, as soon as they are kind of very noise-free and have very distinct boundaries, I could even live if those classes are close together. The larger the noise gets, the more points are spread over the place, which leads to further misclassifications. So small noise. And the third thing I need to take care of is, what do those dimensions tell me? So is dimension 1 and dimension 2, do they span equally well over the feature space? So is one value going from 0 to 1 and the other from 0 to 1 million? So if I take into account that I'm using the Euclidean distance here, I may need to transform my space. So for example, normalizing all being taking values from 0 to 1 or something similar. So this is something I can solve, at least as long as this is kind of not a kind of weirdly distorted space. So if kind of just shrinking one dimension or expanding one dimension would help. So, but this is something important if I work with those classifiers in practice. So the distance function matters. So I can either say the dimension of this band is more important than the dimension of this band, or I could simply scale the space. But this is something which, some information that I need to provide to the system. But except of that, so if the islands, how we call them, or these clusters of data points are well separated, the noise is not too high, and I know something about how those feature values are distributed in space, that's nice. It works well. One further thing, does this approach scale well to large data sets? So consider I'm not doing this labeling here only for a small part of the Rheinauer, but for aerial images all over Germany. So the issue is I need to store a large number of data points. For every labeled example, I need to store one of those data points. In this case, it's simple. It's, let's say, 100 or 200 data points. But if we start having millions or billions of data points, this can be tricky. So the complexity actually grows with the number of data points that I have. If I would fit Gaussian through those 4 clusters, the number of parameters that I have does not grow if I add more data points. So this is something I need to take into account. If I have a very, very large number of those data points, the system may get very slow. Okay? So the nearest neighbor approach works as it's basically a summary of what we told before. So it uses the training data to estimate the distributions, just by saying, just store my training data. And it's kind of a non-parametric approach, so we don't fit a parametric function to our data. It's difficult in the context of presence of noise, so I have a lot of noise. This doesn't perform very well. On the one hand side, we need to have a rather densely sampled space with those data points in order to represent, to kind of reach all areas where my test features in the end, or during the operational phase, my features will actually occur. So I may need to have a large number of training examples. And if I turn that into a discriminative function, I end up having something which is called a Voronoi diagram, which you probably also have seen. So this is a diagram, those lines which have an equal distance to 2 points and those which are closest to that line. So this is exactly the medial axis of those points, and this holds for all points. So this I can represent that as a discriminative function and then saying, okay, everything which falls into this area is assigned to this data point, everything which falls into this polygon is assigned here. This is what's called a Voronoi diagram. Okay, let's say we have some noise in there, want to be a bit more robust against noise. We can easily extend that and say, okay, we don't do a nearest neighbor approach, we do something which is called the k-nearest neighbor approach. So I'm not just looking to the nearest point, I'm looking to the whatever 10, 20, 30, 40, 50, 100 nearest points. And then I can, for example, do a majority voting. Simply say, okay, whatever, 10 of those neighbors tell me it's water, 50 tell me it's urban environment, and it's more likely to be urban than water. But the approach basically stays exactly the same, except that I'm taking k neighbors into account. That's it. Of course, it's also not, it's better to be the nearest neighbor, it's more robust, especially with respect to noise, but again, I have this k, this magic parameter k, how many neighbors do I take into account? If k is very small, then I have the issue that I'm basically less robust with respect to noise I have in my data. If k is large, especially if I don't have a large number of training examples, I may take into classes which are actually rather far away or actually already representing a different class. So it's not free of problems, but it's very simple to implement, very simple to test. I don't need to know anything about the distribution of my features in space. I can just use them as a non-parametric approach, which makes nearest neighbor approaches actually quite attractive for a couple of applications. So that was the simplest classification system, well, probably the simplest classification system you can imagine which is frequently used. So nearest neighbor classification is something you really find out in the field, people working with this classification system. It's actually very simple to implement. So are there any questions about this nearest neighbor classification so far? If this is not the case, you can say, okay, we're done with nearest neighbor classification. Let's look to another classification system which is slightly more complex, so we're increasing the complexity, at least in terms of understanding, now throughout this course today. So the next thing we may look into is so decision trees. Decision trees can be represented as a number of decisions that I do in a sequence. And based on the outcome of a number of decisions, I make the decision what class it is in. Let's say I have a three-dimensional feature vector. I first look only to the first dimension, say, let's say, is this dimension larger or smaller than 0? If it's larger than 0, I proceed asking a certain question. If it's smaller than 0, I may proceed asking a different question. And then I'm asking a certain number of questions, and after, let's say, having asked whatever 5 questions, I say, okay, now it's most likely to be whatever, urban terrain, water, or whatever my example is. So the idea is to kind of ask quotation marks, every new data sample that occurs a certain number of questions, and then decide to which class does it belong to. And I can arrange those questions that I ask as a tree, and that's where the name decision tree actually comes from. So the idea is to have a sequence of splits. So the splits were my questions or decisions. And those splits split up the space in which the features are located And so my goal is to find areas in my feature space which belong to one class. And the hierarchical approach, so I start with one question in the beginning I ask first. Depending on the outcome of this question, I ask a different question, potentially a different question, and proceed until I reach a certain level where I say, okay, I'm now fairly confident or sufficiently confident that my data sample belongs to a certain class. Okay, let's give an example. So let's say we have our feature space. Those squares here is class number 2, and those circles over here represents class number 1. And now I want to create a decision tree, which at every point in time inspects only one dimension of my two-dimensional feature space, so x1 and x2, the 2 dimensions of my feature vector, and want to generate a tree which guides us in how we should make our decisions. Okay, let's look to the elements of such a tree. Tree looks like this. The first node, the top node over here, is always called the root node. That's where everything starts. So this is, every decision starts with this root node. And all those nodes, which are here ellipses, which are so-called decision nodes. And a decision node is a node where I have to make a decision. How do I make a decision? I ask a question to the new data sample. And this is what's written in there. It's also called my test function. And based on the outcome of this test function, it's typically a simple yes-no question, I can actually make a decision and then proceed in a recursive manner. So I start over here and look, for example, to the first dimension of my features, my feature space. And say, okay, is this value larger than a certain threshold? This W10 is a certain threshold that needs to come from somewhere. So if the outcome is yes, it's larger, then I simply ask the next question. Is a second dimension larger than another threshold? You can have a yes-no output. So I can ask a list or a sequence of those decisions. Then I have those nodes, those 3 nodes over here, which are so-called the leaf nodes. This is the end of the tree. These are kind of the leaves. So if you would turn that upside down, you may imagine that this could be a tree. So these are my leaf nodes, and the leaf nodes represent a decision. The decision is which class it is in. So in this case, even after the first question, I already identified that this must be class number 1. Or in this case, after asking the second question, the first output was yes, asking the second question, I can actually distinguish those classes into my box or into my circles. This is the idea of a decision tree. So coming back, again, the decision node implements a test function. The test function is done typically on one dimension of my features, or at least it's done on the features. Quite often one picks one dimension of those features and then makes typically a very simple decision. So those decisions can in theory also be more complex, but quite often I actually can do that with rather simple test functions. And they're decision nodes, or sometimes also called split nodes, because they split up the path of questions that I have to take. Then we have those leaf nodes. The leaf nodes is kind of the end of the tree. So as soon as I reach a leaf node, my sequence of questions that I have to answer is actually done, and I have to make a decision. The decision is it's class number 1, or it's class number 2, or theory could be class number 3, 4, 5, 6. But we can assume 2 classes here, but it works exactly in the same way for multiple classes. So what a leaf node in the end represents is it represents an area and feature space, and the area is defined by those thresholds over here. So because if I'm here in this area, it means I'm in the area where x1 is larger than this threshold and x2 is larger than this threshold. This is kind of an area in this feature space. So every of those leaves represents an area and feature space, and this is the area in which the features are lying that belong to a certain class. And by asking this sequence of decisions, I can actually make a classification. So if I have such a decision tree, the steps that I need to do is actually quite simple. So I start from the root node. If the current root, and then it's kind of a recursive procedure that is recursively executed. If the current node is a leaf node, I simply say, okay, I know which class it is in. I return the class label. Otherwise, and I'm done. Otherwise, it's a split node, and I perform my test function, and then follow to the corresponding branch, so like yes, no decision. And then I go back to 2 and repeat this process until I end up in a leaf node. Okay, so is the idea on how this decision tree works, at least how I can use it given I have one, clear? So we have sequences of decisions, we have a number of decision points. Those decisions are made based on so-called test functions, typically very simple functions, something larger or smaller than a given value. And so I proceed those until I reach my leaf node. Okay, so the next question, once we understood that, how to use it, the question is how do I obtain such a tree? How to obtain such a tree is based, how does the structure look like, and what are the test functions? So let's say I say my test functions are just is larger than a certain value. Then what I need to do is, how do I determine the threshold? Okay. So the next thing we want to look into is how to learn the decision tree. So there are, of course, a large number of thresholds I can actually choose, and finding the optimal decision tree. So it gives me the optimal assignments without asking too many questions. Finding that is actually one of the NP-hard problems. NP-hard basically means the only thing I can solve that is try all combinations and check which one performs best, which is something which is exponentially complex. So it's something I can never do for anything else like a toy example. So the key message in here is it's unrealistic to assume that we have an algorithm that gives me the optimal decision tree. But we can say, okay, maybe if we find a good heuristic, so a good approximation of this optimal, so a good heuristic that leads us to a nearly optimal decision tree. So maybe not optimal, but actually pretty good. So the key question I want to ask is, what could be a good strategy to arrange the split nodes? So which questions to ask and which threshold to choose. Let's say we end the example we had before, we have our two-dimensional space, feature space. What is a good idea on where I should actually make this cut, either in X or in the Y dimension? So what could be intuitively a good idea? Yeah?
The best thing would be to find questions which always divide my points or whatever, my classes, into equal parts.
So you said we should split them up into equal parts. What do you mean with equal parts? So the same size?
Almost, as much as possible.
Why should that be a good idea? Can you motivate that?
Then I get an O, what is it, log 2 or something like that.
Mm-hmm.
I get the smallest amount of steps to actually, at the very end, end up with one.
Okay, so what this will generate me is actually a tree which is not too deep. That's true.
Yes.
But the question is, does this help me to make a good decision? So it's not sufficient to only take into account the number of elements that I have. I also need to take into account the class labels of those individual points. In order to, I mean, you could make this decision, but there's a smarter decision, and the smarter decision takes into account also the class labels. So when can I add a leaf node? Yeah, no, the leaf node. When can I add a leaf node when I build up the tree? I can do that if as soon as all elements in this area represented by this leaf belong to the same class. So maybe a good idea is to split up the space so that on each side of the space I have or as far as possible, only elements which belong to one class. This is something which is often called a purity. So how much purer are the children? So if you have one element, the splitted element is also called children of a node. So if I make a split decision, and let's say all the circles are sitting here and all the rectangles are sitting there, a pretty good idea is to split it in the middle, because then I have one area which is purely populated by circles and one which is purely populated by rectangles. But of course, often it's not that easy. They're kind of overlapping a little bit. But I actually can try to make a split so that there's just a very small number of circles in the area corresponding to rectangles according to the split node, as well as the other way around. And this leads to a measure of impurity. So impure class is if I have whatever the same number of elements of class 1 and class 2 in my set. So let's say I have 100 elements in my current area, 50 of them are circles, 50 of them are rectangles. That doesn't help me a lot, this split. It would be better to split it in a different way, that let's say the distribution is 90, or so that on each side, on one hand side is, for example, 90 to 10, and then the other way, exactly the same way, 90 to 10%. Because then I split that up so that the majority of circles are on one side and just a small number of rectangles, and so on. And there are different ways on how to measure this impurity. So the two most popular ones are the so-called entropy and something called the Gini index. First I would like to look into entropy and tell you how we can actually use the entropy for finding good split nodes. So what is entropy? Entropy is a measure of uncertainty in a probability distribution. So what we have here, if we have two classes, is we can see this as a probability distribution of my two elements. So let's say the entropy of my class set, so this now, the notation is slightly suboptimal. So these are the classes we have within one area, so it's not the whole number of classes. So I go through my area and check all the elements in my area and say, what's the probability of this element times the log of this probability? And if you have a binary decision, so we have just, let's say, two classes, so it's binary. So we have just what's the probability for class 1 and what's the probability for class 2, where the probability for class 2 is 1 minus the other probability. Okay, so let's see here. Let's say we have 100 elements in my current area, and 10 out of this 100 elements belong to class number 1. That means I have a probability of the first class is 10%, the other is 90%. But I plotted here is the probability of the first class. So if the probability of the first class is 10%, 0.1, I will get this entropy value. So what you can see on this entropy curve is the closer I go to the borders, the smaller the entropy gets. So if it is kind of nearly 0, it means there's a 0 probability that or near 0 probability that in this area there's an element of class 1, I get a very low entropy value. So it's a small impurity. If, however, the probability is 50%, that means in this area 50% of the elements belong to class 1 and 50% of the elements belong to class 2, I have the maximum entropy value. Okay? So is the idea of entropy clear? So this, if I have two classes, simply P of class 1 times log of P of class 2 plus 1 minus of the probability of 1 minus the probability of class 1, because it corresponds to the probability of class 2 and the log. So maybe I write that down. So for the binary case, the entropy is P of class 1 type log ln of P of class 1, sorry, minus P of 1, okay, let's make it P of W2 times P of W2, which is minus P W1 P of W1 minus 1 minus P of W1. Of course, this is equal to P of W2 times and 1 minus P of W2. Okay? And, oh yeah, W1, sorry. And so what I plotted here is this P of W1, this plot, corresponding to this element. What you can see is, if it's more or less 50-50, if I choose a random element from this area, if it will be class 1 or 2, it is in high impurity, in high entropy. If I'm pretty sure it's class 2, or I'm pretty sure class 1, or pretty sure it's class 2, then it was a very good split because it allows me to do this split. So what I do is I actually define a measure of the kind of change in impurity by taking into account the impurity. So I'm interested in the change in entropy. So I'm adding a new split, and how much does it change my impurity? So the change in impurity is the impurity I had before, and then minus an element over here, which is basically says what's the impurity on the left side of my tree, and what's the impurity on the right side of my tree after the split. So this is both after the split, and times the probability that I actually end up if I draw a random sample. So basically how many samples, how many data points go to the left or to the right. So left and right means here I have my split node, and this is left and right, before called no and yes. So this is all the elements omega, this is omega left, and this is omega right. So I say, okay, what do I have before? If I would stop here, and then I add those two guys and say, what's the impurity on the left and the right-hand side? And my hope is that the impurity is large in here, and afterwards is small. Okay? So is the idea clear on what we are trying to do with this strategy? Again, this is not an optimal strategy. It's a heuristic, because the optimal solution would be NP hard. So we can't compute it in practice. So this is a heuristic, which you say, we do that, we actually come up with pretty good decision trees. With having the goal that with every split that we do, we maximize the purity or minimize the impurity. So we want to get more purer sets, purer areas after the split. Okay? So this entropy is a measure which comes from information theory. Shannon introduced that. There are other ways for measuring impurity, and one was proposed by Gini as an alternative criterion, or it is an alternative criterion to entropy. It's called Gini index, which is basically 1 minus the sum of all classes and the squared probabilities. So in our case, it would be 1 minus the probability that we're in the class left and class right, both squared. But if you look to those functions, this is the curve for the entropy, and this is the curve for the Gini index. So the key take-home message, there are different measures to do that, but this is kind of a very similar shape. And so they end up in obtaining or resulting actually in very similar decision trees. But they are kind of different ways in how we can add that. Okay, now what we know is we want to build up a decision tree, and we know at every point in time which decision we should actually do. Right? Just look to all splits we can do and select the one which performs best under our impurity measure. So the next thing is, when should we stop? So when should we add so whenever we add a leaf node, we should stop. And in the standard case, at least those decision trees which I have shown here, I would stop if I have a kind of pure regions, so they are only elements of one class in there. What could actually be problematic about this strategy if I do that? Yeah?
This might not include other elements of the same class, but being in a different right or left area. So I exclude part of my class, although they belong to the class.
I exclude part of the class, although they belong to the class. I think don't fully get that.
I've got one on the left side,
Yeah.
for example, which is pure, but I still have the same few elements of the same class in the right one.
Yeah, but there's nothing bad about that. In this case, I would add here a leaf node and would continue to split here, to split nodes, until I'm pure and then add all my leaf nodes down here. So if I end up here, I'm already done, and here I would need to go deeper through the tree. That would not be a problem. It has something to do with what we discussed in the beginning with the issue of generalization. What happens if I kind of break up this tree until all leaves are completely pure? What I'm basically doing then, I'm kind of overfitting to my training set. So it's very likely unless my training data is perfect, it's free of noise, I'm very likely to do an overfitting over here. So this leads to an overfitting of the tree and is unlikely, at least in most practical applications of this approach, to generalize well to other data sets. So at some point in time, I should not split that up to the smallest element. It's better to say, okay, it's pure enough an area that I say, okay, this is a certain label or this is a certain label with a certain probability. So I simply don't proceed up to the bottom level where every error is completely pure, because if I have a few noisy samples in there, this will lead to some potentially weird splits that I have. So what I typically do is I have a certain threshold that if my Gini index is whatever, smaller than 0.05 or larger than 0.95, then I say, okay, I'm done. This area is reasonably split up, and everything which is in there is supposed to be supposed to belong to the class which has the most elements in that area. It's just taking into account that my training data set is potentially noisy. So if we kind of sum up decision trees for classification. So the nice thing about decision trees, they are comparably easy to understand. You can quite intuitively understand how decisions are made. So you have a number of questions you ask to a new data sample, and you proceed through that and obtain splits based on those decisions. At some point you're done. You can even nicely visualize a tree. You can really plot it as a tree. If the tree doesn't have whatever 20, 30, 40, 50 levels, you can actually plot that very well and get a quite nice idea of what are important features, what are important dimensions, what are not that important dimensions. It works very well even in high-dimensional spaces because we treat every dimension separately, for example, do a split in all those individual dimensions, and it works out very well. And I can even do things which can be critical for other techniques. If I say I have a few dimensions which have discrete values and a few dimensions which have continuous variables. For example, if the day of the week matters for the classification task that I'm doing, I kind of have a split up in whatever Monday, Tuesday, Wednesday, Thursday, and so on, and other dimensions are continuous variables. It's perfectly, very easily doable with the decision tree. It's also one of those nice things. But again, finding the optimal tree, optimal split is NP hard, and therefore we typically use heuristics such as entropy or Gini index are probably the two most popular ones. Okay, is there any question about decision trees at the moment? Or are you think you can all implement a decision tree in MATLAB? So you have data, you should generate such a tree. Do you feel able to do that? That would be my goal. Of course, it's nothing you do in 10 minutes, but you should have understood that sufficiently well that you could reproduce such results. That's at least my hope. If this is not the case, please ask questions.
Well, I think it's one thing to understand the principle, and it's another thing to find the right questions for the data set you're going to evaluate.
Yes, this is true. So what are the right questions? I would start here with defining very simple questions. Something is larger or smaller than the threshold. Then you can simply vary your threshold until you have the maximum or the minimum impurity. There was a second question. Oh, this is very simple. I'm just counting how many elements of class 1 and class 2 are in this area. So if I have 100 elements in my area and 60 of them belong to class 1 is 60% probability and class 2 40%. That's very easy. Well, just for the recording, the question was how to obtain the probabilities. Any further questions? Okay, if this is not the case, make a 5-minute break, let some fresh air in, and then continue with maximum a posteriori classification. Thank you. Okay, I would now like to continue with maxima posteriori classification, and or also called MAP classification in short. And this is an approach which makes the assumption that classification, or not makes the assumption, that claims that classification, kann ich Ihnen was helfen? Yes. Which makes the assumption that classification is simply decision making. So I have to make a number of decisions, and the decision is basically assigning a class to a certain feature. And what maxima posteriori classification does is it uses probability theory in order to support the decision-making process, and actually does this based on Bayes' rule. So Bayes' rule is a central element for maximum a posteriori classification. So you should have all seen Bayes' rule, which looks like this. What is the probability of a class given a feature? And this is a question that we have to answer. So my function, my input function, gets the feature, and I want to provide the corresponding class. This can be a probability distribution over the class, or it can be, let's say, the most likely class. And what Bayes' rule tells me that I can transform the probability of my class given the feature, that's what I want to have because I have the feature, I want to obtain the class, into a statement which says what's the probability of that feature occurring given I know the class times the prior probability of my class times the evidence, which is what's the probability that this feature occurs in general. Okay. So again, going to this. What this is the prior or the a priori probability for the occurrence of the class given I don't have a feature observation. So if I go to my circles and my rectangles from before, then it's simply what's the number of rectangles in the space at all and the number of circles without ever having inspected my features. This class down here, something which is also called the evidence, is a probability for a feature occurrence. And the nice thing is it can quite simply be obtained by simply using this rule over here. So I reduce this to this expression over here, iterating over all classes. That means I don't need to do more computations. It's not a quantity that's hard to estimate for me. I can transform it in this way, and then these elements I anyhow need to compute, and these are actually those elements here of my sum. So it's no extra computation in that sense. And I have this term over here, which is typically called the likelihood function, also called the observation model. So it's the likelihood function for the class omega. So what is the, given I know my class omega, what is the probability that this feature actually occurs? And again, there's also something called likelihood times prior divided by evidence. And quite often, as this evidence is the same for all classes, it's typically also written as a normalizer. So this evidence is simply written as a normalizer. We can treat that as a constant, because if I have my feature, this element is the same for all classes, So you can just say, this is just a constant which is the same for all classes. So in the decision-making process, I may not need to take that into account. So then I have my likelihood times my prior. These are the elements I want to look into. Again, just kind of, to have everything on a single slide. We have here, this is the class probability. Given an observed feature, that's what I want to have. But computing this is typically tricky. Therefore, I use Bayes' rule to switch that around. This is a sensor model or observation model. The probability of observing a feature given a class, and this is much easier to obtain from training data. This is the prior probability for the occurrence of a class and something which is basically a normalizer. So those two elements over here. So this is a normalizer. It's the same for all classes. Those are the two quantities that I need to compute, that I need to know in order to have that. So if I learn a classifier, a map classifier, what I need to do is I need to learn those two probability distributions. That's kind of the key thing I need to do. And if I do that, map classification actually gets pretty simple. It's a two-step process. I apply Bayes' rule, and I said here, again, this is identical for all classes, thus it can in the end be ignored for decision making. So I can just say this element is proportional to what's written here, top. And then I simply select the most likely class. So I select the class Wi star, where I star is argmax over the different classes of this expression over here. So best class, likelihood times the prior that I want to have. Okay, now obviously this depends on how these probability distributions look like, right? This is a very complex probability distribution that may be hard to obtain. If these are very simple probability distributions, maybe just simple histograms, that's much easier. And therefore, I would like to look into the case on how does map classification actually looks like with Gaussian distributed features. So my feature E is now a continuous variable x, and this continuous variable x, given the class, is distributed according to a Gaussian distribution. As a result of that, we can simply rewrite the expression over here, the expression I'm interested in. And here I have my Gaussian distribution. Okay? So in order to evaluate this expression, it's often easier to go into the log space. This is a Gaussian distribution. And so I can actually, because if I'm taking into account a maximization problem, so if I want to maximize a function f, I can also maximize log f as a monotonic function, or I can minimize the negative log of that function. It's exactly equivalent. And therefore, we typically take into account the negative log likelihood, so minus log of that function is simply minus the log of our normalizer, minus the log of our Gaussian distribution, minus the log of our prior. Okay, as a result of that, the maxima a posteriori approach, where I wanted to maximize this expression over here, is the same as minimizing this expression over here. The reason for that the normalizer goes away because the normalizer is the same over all classes, so I don't need to take that into account. Therefore, I can actually skip that, and then this is the result that I obtain. Is this kind of clear? So are you all happy up to this point? All on board, let's say it that way. Maybe not happy, but on board up to this point. So who has an issue with this? All fine? Some reaction would be very helpful. Okay, so what we have done so far, let's repeat that. We started with Bayes' rule in order to simplify the expression P of class given feature. That's what I want. And the probability of being in a certain having a certain class given my feature. I use Bayes' rule to simplify this expression. into the probability of the feature occurrence given the class times the prior probability of the class. I dropped the normalizer because I said the normalizer does not depend on the class. So if I make the decision which class is the best one, I don't care about the normalizer. And I said in order to further simplify that, I go into the space of negative log likelihoods. So I just make minus log of my expression, because if I maximize want to maximize a function, I can equivalently minimize the negative log likelihood. So log is a monotonic function, and I can, if I maximize a function f, I can also minimize the negative function. Okay? So that's all we did so far. And then we end up with this expression, under the assumption that this is a Gaussian distribution. So we made this assumption that this is Gaussian, although we haven't really exploited that yet. We have written it here, but we haven't exploited that. So it could also be, G could also be a different function in theory up to that point. But we will use it in a minute. Yeah?
What is the advantage of minimizing the negative log to maximizing the positive?
This doesn't make any difference. It's just kind of often, this comes from the fact that this is often formulated using optimization techniques and error minimization techniques, and there you always minimize an error. And this is just kind of how it is formulated, but it doesn't make a difference. Mathematically, it doesn't make a difference. Okay, so everyone on board up to this point? Okay. Now we can say, okay, what we can do is now, if we have two classes, we can basically say, okay, I look into this expression, or basically this expression, and say, we define a function that is p of class 1 given x minus p of class 2 given x, or the other way around, minus p of class 1 given x plus p of class 2 given x. Right? I can just define this function. This is what I've done here. So, and at the position where this function changes its sign, so it goes from minus to plus or from plus to minus, this is exactly the decision boundary, where the probability for one class is higher, whatever, on its left-hand side than on its right-hand side. So they swap. So where this function changes its sign, this actually defines, so d equals 0, where d equals 0 when on the left and the right-hand side is class 1 or class 2 larger, this is actually my decision boundary. So this defines, this function d can be used to define my decision boundary. Okay, now let's simply expand this expression. We just take the definitions of these expressions over here and put it into our function. So this was log of the of my Gaussian corresponding to class 1 minus the log of the prior plus the same for class number 2. It's just filling those expressions with life. Okay? Everyone happy till here? Okay, so the next thing I can then do, okay, now I can simply exploit that these guys are Gaussian distributions. These are Gaussian distributions. I can actually simplify this term to this expression. So this is the exponent of the Gaussian number 1, the exponent of the Gaussian number 2, and then the two priors I keep exactly the same over here, plus some constant, which is the result of the part in front of the e to the power of. Okay? So everyone happy up to here? Any questions about this transformation? Okay, so I can now simply rewrite that function as a quadratic function. Now this expression over here, can just by rearranging those terms, I have one element here where it's quadratic in x, it's linear in x, and this is a constant. Right? And I have my two matrices sitting over here, and also those elements here in the linear term, plus some constant. if you have this kind of shape, then the shape of this, where the decision boundary changes its sign, basically depends on the eigenvalues of those two matrices, because these are the elements which are involved in here. You can actually plot that and say, okay, if these are my two Gaussians, so just say these ellipses correspond to the covariance matrices located. There's those two locations. This is class number 1 and this is class number 2. Then this curve over here represents my decision boundary. So all data points which fall into this area will be assigned to class number 1. Everything outside here will be assigned to class number 2. Because these are the points, where these are kind of the Gaussian distributions of feature occurrences given the class. So these are feature occurrences given the class. Then this turns into my decision boundary. So everything which is in there will be assigned to class number 1. Everything will be out there will be assigned to class number 2. And depending on how they are arranged, I get different decision boundaries. So if we have a large overlapping area, this will be the decision boundary. Everything which sits in here will be assigned to class number 2. Same holds for this area. And everything which sits in here are the things which are assigned to number 1. Okay, no, that was one too much. Okay, so this was done for the simple case of, no, for the case of Gaussian distributions. Just now skipped now, I had some extra slides here. What happens if this is a discrete variable? But in interest of time, I'm going to skip that for the moment. So what we have now, we have kind of the methodology on how to do classification with this system. The only thing is, what we need to know now is, how do we learn the distribution of features that gives us then our discriminative function d? In order to obtain that, what do we need? We need the mean and the covariance matrix of these Gaussian distributions. So the question is now, learning these parameters basically turns into estimating the mean and the covariance matrix that we have. So now the step is actually learning this classifier. We define the classifier now, how it looks like mathematically, and now we want to learn this classifier. So both of these guys, the probability of seeing a feature given I know the class, and the prior probability of the classes are not known, so we need to learn it from our data, so from our training data. So we need to use the training data in order to fill those two distributions. Again, if they are Gaussian, it boils down in estimating the mean and the covariance matrix. So what I have is, I assume to have the sample size is n, so I have n training examples, and I have ni samples corresponding to the class wi. So whatever. n1 is the number of elements of class 1, n2 is the number of elements of class 2. So let's start with the prior distribution. So how to obtain the probability for that prior distribution? So the probability that the class 1 occurs, the probability that class 2 occurs if I don't have any observation. How do I obtain that?
Well, if you have no observation, you can't count.
No, I have training data, but it's assuming, so I want to compute this distribution without giving the feature, that's what I meant. Of course, I have my training example, I have my labeled training data, and from this labeled training data, I want to compute this distribution. How do I do that?
Well, you just count.
I just count. So just say, the probability for class, actually, here, an I is missing here. The probability of class number 1 is the number of occurrences of class 1 in my training data divided by the number of training examples that I have. And the probability that class 2 occurs is the number of training examples from class 2 divided by the overall number of training examples. So that's Very straightforward. Okay, let's go, okay, skip over that to the case if you have a Gaussian distribution. So if you have a Gaussian distribution, you said, okay, this probability distribution, the occurrence of my feature given the class is a Gaussian distribution. That's what we said. What I can do is I simply take all the features which belong to class I. Let's just not iterate over them, therefore, these two indices. So this should be all features corresponding to data points belonging to class I. I simply compute the mean over all of them. And then I is simply the number of elements of class I. So just take all the data points that I have where I know from my labeled training data that they belong to class number 1. I simply compute the mean. It's very easy. Just split my training data set into two parts. The one which belong to class 1, the one which belong to class 2. And then what I do, I compute the mean for class 1, the mean for class 2, and then exactly in the same way, the covariance matrix of class 1 and the covariance matrix of class number 2. And that's it. I don't need to do more. So once I understood that framework, that everything boils down in maxima posteriori classification to, for the Gaussian case, for estimating the mean and the covariance matrix for the individual classes. I just need to separate my training data into those which belong to class 1, those which belong to class 2, compute the mean and the covariance matrix, and that's it. Then I have my distribution, and the rest is easy. This drives me towards the end of this approach of classification in general, and I just want to make one distinction, or just explain one distinction which is often made between parametric and non-parametric approaches. So parametric approaches try to estimate a parametric function, for example, the distribution of our classes to the data. This is what the map approach for the Gaussian case does. So we fit a parametric function, a Gaussian distribution, through our data. In contrast to that, there are also non-parametric approaches. The non-parametric approach says, I know too little about my feature distributions. I don't want to fit a Gaussian or another parametric function to it. I just use the data as it is as a representative for the distribution. That's what the nearest neighbor approach does. It simply says, I simply store all my training examples and I don't explicitly represent a probability distribution. And these are kind of the two general ways that how we can actually solve that. And non-parametric approaches typically have the issue that they grow with the size of the training data that I have. The larger the training data is that I have, the larger or the more complex those models get. So they may not scale up to very large sizes. If I know everything is Gaussian, I have thousands of training examples, then I'm actually, the complexity of my model does not grow. Because I just fit a Gaussian distribution through it and I'm happy. The question is, do I need then thousands or millions of samples if everything is Gaussian? But that's a different story. So the non-parametric approaches grow in size as the training size expands. And this also leads us to another distinction that is often done between generative and discriminative approaches. So what the so-called generative approaches do, they typically model the full probability distribution, and this also, if I know the parameters of my probability distribution, for example, of my Gaussian, this allows me also to kind of generate new data and new features which are likely to occur. I can just sample from this distribution. If I have a Gaussian, I can draw random samples according to this Gaussian. And so they typically estimate the probability distribution and then estimate the decision boundary. And the discriminative approaches, they just have this, they don't try to estimate this distribution, but they directly estimate the discriminants. So often this is easier to do, but this gives me typically more flexibility if I know the full distributions. And I can even sample new data, sample potential features from those distributions, which can be advantages for some of the techniques. Okay, so this brings me to the end. What have we done? We've done an introduction to classification. We started with that 2 days ago. What you should know is how to build a simple classifier. What is important in classification? How to evaluate a classifier? What are different types of errors that I see? What does generalization mean? Then you should know how nearest neighbor classification works. You should also know how decision trees work. I want you to be able to build a decision tree on your own. It's one of the goals. Then we looked into maximum posterior classification. What I skipped in, so what I've done here is it's for the Gaussian case. What I skipped in the interest of time now was to do that for the discrete case if I have discrete variables. Then it's typically even easier than for the Gaussian case. And now the last thing I want to do is I want to show a few slides on what you can do with classifications from different areas. So one of the things that we discussed is actually estimate land use from remote sensing data, for example. So we have this satellite data with different spectral bands. We want to make a classification how this land is used based on the spectral signal that I get from those images. So once I get the satellite data, I can very well estimate, for example, how the land is used on a really large scale without asking anyone. So I get the semantic interpretation directly from those satellite images. And I can obtain that very efficiently on very large scales without being a human sitting here labeling the individual fields. That's a very important application. Now we're moving to a completely different application. You may know the Kinect sensor you have over here. So some of you who have an Microsoft Xbox also know this sensor, which actually perceives you, and you can use your body basically as your game controller. What this approach does, it classifies, so this is a depth image, it classifies this depth image into different body parts and uses this to reconstruct your posture. And what this uses is an advanced version of decision trees. These are so-called random forests, which is just kind of a large set of decision trees in order to do that. And they trained on a very, very large number of postures, so 1 million test images with the posture given, trained this random forest, which is kind of, see that as an advanced decision tree or a large set of decision trees. And then we're able very efficiently on the device itself actually do the classification, classify what's a hand, what's an elbow, what's my shoulder, and this way estimate your body posture when you're doing your game, playing games. The other thing you probably also have seen, if you have your digital camera or your mobile phone, you make a picture with it, it sometimes highlights the faces of the people. There's also a very classical or standard classification problem is simply face detection. The approach to do that is actually very easy, or not very easy, but surprisingly simple. Is use very simple features like how many darker pixels are with respect to brighter pixels. So it's kind of different types of features of that size, so-called HAR-like features. And then they have run one classification approach which simply tries to combine very simple classifiers, somehow related to the decision trees, but using that in a different way. It's the so-called boosting technique, in order to detect all those faces in a large variety of different images. So whenever you use your mobile phone or your digital camera to take pictures and it estimates the faces in the image in order to get a good focus, they're using exactly those classification approaches. So it's a very, very widely adopted technique. So this was presented, I think, in the beginning of 91, beginning of the 90s, and is one of the very, very frequently used classification techniques. The advantage of this technique especially is that learning takes a while, but it's very efficient to be computed even on an embedded device, on a small-scale device. That's it from my side. I just after the summary tried to show you a few examples where classification is used, and it's very, very widely used in technical systems of any type, in your mobile phone, in a very large number of settings where some interpretation of image data needs to be done. In terms of books, so far the script was the main source of the books. So there's actually this book, this Apayadin approach, which is called Introduction to Machine Learning, where those chapters address the classification problem. I found this book extremely easy to access. I can just recommend looking into this book if you want to read further through it, because everything starts in 1D, generalizes to ND, and I found it the most easily accessible book on classification from my personal experience. So if you want to look into that, or if you want to have a book where you want to read over that again, and you're not happy with the script, I highly recommend the Apayadin book. That's it from my side. Thank you very much for your attention, and see you all next week. Thank you very much.